Hello and welcome to lecture number 10 on Jacobians. The Jacobian relates the end effector velocity and the joint velocities. So when a robot is moving, or how do we move a robot, we basically give power to the motor, which is connected to the joint. Now the motor rotates, because of which the joint rotates, and when the joint rotates, the end effector moves. And the Jacobian relates the velocity of the end effector and the joint, and it also tells us very important things like singularities. Okay, so are there singularities? Where are the singularities? And further, when we are trying to minimize the energy of the energy consumed by the motors while doing a task, the Jacobian also gives us an idea of what is the energy consumption. So this is a very, very important concept of correlating the joint velocity and the end effector velocity. So today our topic is on Jacobians, and let us try to understand how a robot works, or how a robot functions. So a robot essentially will consist of joints. So we have joints, we have links, and each of the joints are connected by an actuator. So we have an actuator, which is basically a motor. Then we have an encoder, which is a position sensor, and we have a gear in front. Now this kind of control or structure is called independent joint control. So this is called independent joint control. And how it works is essentially we are going to give a voltage to the motor. The motor is going to rotate. The rotation will cause a change in theta, and this will cause a change in x and y there. So it is this is how the robot essentially moves in space. Now, what we are seeing here is that the input to the motor is volts. Now, when the joint rotates, it rotates in degrees, and when the end effector moves, this is in Cartesian coordinates, which is in meters or centimeters. Now, all these three are different units. So basically, if I draw it here, so we have the voltage to the motor, which is in volts. The voltage to the motor will cause rotation of a joint. So this is in degrees. So this is my theta. And then the output of this is my x, y, which is in centimeters or meters. Now this basically shows that there is some mapping which goes on from the voltage space to the joint space, and from the joint space to the end effector space. Now, is the mapping 1:1? Is it many:1? Okay, and does funny things happen that the mapping, if you give a particular voltage to the motor, the joint will rotate, but the end effector will not move. Can that happen? Now that also can happen. So which basically means this some velocity at the joint is going into the null space. Okay, so what we are trying to understand here is when we are trying to control the robot, we also need to know what is the relationship between the joint velocity and the end effector velocity. Why? Because at the end of the day, we are going to control the joint velocities, right? So how do we find the relationship? Now we can find the relationship by looking at the geometry of the linkage. Now in terms of geometry, what I mean is we have seen that we have, if I were to draw a two-link system here, so we have one link here, another link here. Okay, so this is my theta1 and this is my theta2, and this is xy. Okay, this is L1, L2. So geometrically, we can find the relation between x is equal to L1 cos theta1. This we have seen quite a few times earlier, L2 cos theta1 plus theta2. Y is equal to L1 sin theta1 plus L2 sin theta1 plus theta2. This gives a position relationship between the position of the joint and the position of the end effector. So I can write this as x is equal to a function of theta1 and theta2. Okay, so this gives a position relationship. Now if we have a relationship like this, let me look at the general case where y1 is a function of x1, x2, x3 like this up to x6, just for example, and y2 is a function of x1 similarly up to y6 is a function of x1 like this. What we can do is if I want to calculate the differentials of y as a function of the differentials of x, then we can write this as del of y1 is equal to dou of f1 by dx1 to d of x1 plus del of f1 by del of x2 to d of x2 plus like this, right? Now similarly dy I can write as dy2 is equal to del of f2 into dx1 del of x1 like this. Okay, now so proceeding in this way, what we see is that we can find the differentials of y as a function of the differentials of x. Now in our equation that I just wrote, I need to find, if I want to find the velocity from here, I need to find the differentials of x and y with respect to the differentials of theta 1 and theta 2, right, in this equation, right? Now we can write this as d of y is equal to d of f into del of x into dx. Okay, we can write it in this way, and this is what we mean by a Jacobian, so we can write this as j of x into del of x. Now this term is what we call the Jacobian. Okay, and even shorter, I can write this as y dot is equal to j into x dot. Now this is called the Jacobian, okay, which is basically relating the differentials of y and that of x, right? So what we are interested in is to find the differentials of x and theta for our manipulator case, and what we do is basically I take the derivative of these two, this equation and this equation. So that will give me the relation between x dot and theta dots. Okay, so what we do is I come back here again and we draw our two-link manipulator just to understand. So here is this is my x-axis, that's my y-axis. This is L1, L2, theta 1 and theta 2. This is xy, right? So as I wrote earlier, x is equal to L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Y is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay. Now I'm going to take the differentials of x and y with respect to theta 1 and theta 2. So how many variables are there? There is in these two equations we have theta 1 and theta 2. Okay, so x is a function of theta 1 and theta 2, and y is also a function of theta 1 and theta 2. So first what I'll do is I'll take the derivative with respect to theta 1, then I'll take the derivative with respect to theta 2. So if I do that, then I can write this as d of x is equal to minus L1 sin 1 minus L2 sin 1 2. So I take the derivative of this with respect to theta 1, then I take it with respect to theta 2. So this does not have theta 1, this has this does not have theta 2, this has theta 2, so it becomes minus L2 sin 1 2. Similarly, I take the derivative of y, dy is equal to L1 cos 1 plus L2 cos 1 2. Okay, and then with respect to theta 2, it becomes L2 cos 1 2. Okay, I'm writing it in matrix form. So this is d of theta 1 and d of theta 2. Okay, so this is my position relationship. So this is position and this is velocity relationship. So this is not average velocity. Please note that this is incremental velocity. Okay, in terms of dx and dy. So this is incremental, this is not average velocity. So this here now is a 2 by 2 matrix, 2 by 2, and this is called the Jacobian. Okay, just exactly similar to what we had done here. And how do we get the Jacobian is how what I explained. Okay, so from the position relationship we're getting the velocity relationship, and I can write this similarly, x dot is equal to j into theta dot. So this Jacobian relates the joint velocity with that of the end effector velocity. Okay, so now when we are controlling the robot, we said that we are controlling the joint. We are not directly controlling the end effector. Okay, so in order to control the joint, so this is the same equation, x dot is equal to j into theta dot. So for control, what we need we need to control theta 1, theta, okay, at the joint. So when we're controlling the joint velocity, then we have a particular end effector velocity. Now suppose for a given or desired x dot, what would be theta dot? That means for a desired velocity of the end effector. So my end effector is here, and I want this to move at x dot is equal to 1 meter per second, and y dot is equal to say 0, just for example. Okay, Now for this, getting this end effector velocity x dot y dot, what should be the corresponding theta 1 dot and theta 2 dot? That is what I need to find out, because that is what the controller will have to enforce, right? So now from this equation, if I take the theta dot is equal to J inverse of x dot, okay? So for a given end effector velocities, I want to find what is the joint velocity, and for doing that I have to invert this equation. Let's call it equation number 1, okay? Now you find that theta dot is equal to inverse of is adjoint of J divided by determinant of J, okay, into x dot. This is what we are getting. Now this gives us the relation between the joint velocities and the end effector velocity. Now the determinant of J determines the relationship between x dot and theta dot. So what we are seeing here is that if determinant of J were to become equal to 0, then theta dot implies that theta dot, okay, will become equal to infinity, right? So theta dot becoming infinity means what? Means infinite velocity. So this means infinite velocity. Now obviously a motor cannot give infinite velocity, okay, because to give infinite velocity it requires infinite energy now. So what we see is that these are related now. So to give infinite velocity you require infinite energy, right? So what we are seeing is this determinant of J is an indicator of how much energy you require. Now this point where the determinant of J becomes equal to 0 is also called the singular point, okay? Now this is called a singular point because the manipulator cannot go to this point, because to go to that point you require infinite velocity and infinite energy, which the motor does not have, okay? So these points are called singular points, and we can compute them from the Jacobian. So what the Jacobian tells us, gives us the relationship between the energy, okay, but the Jacobian also tells us about the singularities of the mechanism, and singularities are points where the determinant of J is equal to 0. Now the singularities, how do we find the singularity? Let's look at the Jacobian. So basically finding singular points. How do we find singular points? To find singular points we have to look at the determinant of J, okay, and which means I take the determinant of minus L1 cos 1 minus L2 cos 1 2. This is the determinant we derived just some time back, and L2 cos 1 2, here it is L1 sin 1 plus L2 sin 1 2, and here it is L2 sin 1 2, okay? Now if you find the determinant of this, it means multiply this into this minus that into that. What is surprising is that what it will come out is L1 L2 sin 2. What happens is theta 1 gets cancelled out. So it is very interesting to note that this determinant of J depends only on L1 L2 and S2. Now L1 L2 are fixed because they are linked lengths, because they are the lengths, okay, so they cannot change. So what is the variable is theta 2, which means that the variable is theta 2. So now if you want to make determinant of J equal to 0, then it basically implies that L1 L2 sin 2 must be made equal to 0. Now L1 cannot become equal to L2, cannot become equal to 0 because they are linked lengths. So the only possibility is sin 2 becoming 0, okay, which means theta 2 is equal to 0 degrees and 180 degrees, okay? So these points are called singular points, okay? So now what we see is that for a two-link manipulator we can find singular points, and these singular points are given by are found to be at 0 and 180 degrees. Now let's see further that where in the manipulator workspace is this. So this is my two-link manipulator, okay? The manipulator workspace of this is a circle that we know, okay? So if L1 is equal to L2, then inside there is nothing. So L1 is equal to L2. So L1 is equal to L2. So where is theta? This is my theta 1 and that's my theta 2. So some things to note about singularity is that it does not depend on theta 1. So theta 1 can take any value, that's what it means, okay? Now for theta 2 equal to 0 degrees, and 180 degrees. What is the positions? So one of the position is the fully, let me draw it in some other color, it is fully stretched position. So it is fully stretched here and here. Okay, so this is one position corresponding to theta 2 equal to 0. So theta 2 equal to 0 degrees corresponds to this position, which the point is here. Now because the point is here, okay, and theta 1 can vary from 0 to 360 because it has no effect on singularity. So what we are getting is this boundary like this. So if you can imagine, for theta 2 equal to 0 degrees, the arm is fully stretched, and when we rotate theta 1 from 0 to 360 degrees, what we get is the boundary. Okay, so what we're getting, the point is actually a boundary point, and this boundary point is called the boundary singularity. So singularities are of two kinds. Okay, one is called the boundary singularity. So the boundary singularities all manipulators will have because they cannot go out of that boundary. So that point in a way is a singular point. Okay. The other is the inside workspace singularity, which is also called the interior singularity. Okay. Now interior singularity would be inside. Now in this particular case, we have seen for theta 2 equal to 0. Let's look for theta 2 equal to 180. What happens at 180? Now at 180, what happens is this is fully folded. Okay, so this is fully folded and it comes here. So it's a point there. If L1 is equal to L2. Okay, so if L1 is not equal to L2, if L1 is not equal to L2, then what will happen is you'll get another small region inside. Okay, that means inside here it cannot go. Those are singular points again. So interior singularities are inside the workspace. Okay, so there are two kinds of singularities where one is on a boundary, which is called the boundary singularity, and the other is an inside workspace singularity. Now the 2 degree of freedom manipulator, as we have seen, where N1 is equal to L2, okay, it does not have an interior singularity because this is the point here, okay, and it can go everywhere else. Okay, so but some manipulators can have interior singularities also. Okay, higher degree of freedom manipulators do have can have interior singularities. So this is the definition of what we mean by a singularity, and we can get an idea of the singularity by looking at the Jacobian. Now what we saw is we derived the Jacobian this way, and because the Jacobian here is 2 by 2, okay, we ended up with L1 L2 sine 2. Something very important is that it does not depend on theta 1. Now something more important here, or let's just go back and look at this. So we basically said that this is velocity, angular velocity in radians per second or degrees per second. This is the end effector velocity in meters per second. Now what this basically tells us, determinant of j equal to 0, is that if you need determinant of j becoming equal to 0 means velocity becomes infinity. Now infinity means infinite, velocity means infinite energy. So this is also an indicator of energy, how much energy is being consumed, because velocities are an indicator of energy. Okay, so for example, if you want higher velocity, you have to give more energy. Okay, so based on that, the Jacobian is also an indicator, determinant of j. So determinant of j is also an indicator of energy consumed. So determinant of j also indicates energy. Okay, now this is very interesting because it tries to answer the all-important question that if you have a manipulator, again let's take the example of two-link manipulator. Okay, now we want to what is the work volume of this manipulator? It is circle. Okay, so if this is the work volume of the manipulator, then where must you perform the task? The task must be inside the work volume, of course. Okay, you cannot perform the task outside, that's not possible because the manipulator cannot go there. But inside the work volume, where would you perform the task? Would you perform it here? So I want to pick and place. Should I do it here? Okay, pick and place here. Should I do it here? Okay, pick and place like this from here to here. Should I do it here? Okay, so what should be done or where it should be done? So the way to answer this is where task should be done where energy requirement is minimum Okay, so this makes sense that the task should be done in a region in the workspace where the energy requirement is minimum. So now we saw that if determinant of j goes to 0, determinant of j goes to 0, then energy goes to infinity. Okay, so if determinant of j is maximized, okay, then energy is minimized. Okay, and this makes sense. So if determinant of j becomes equal to 0, energy goes to infinity. But if determinant of j is maximized, then energy is minimized. Now we know that determinant of j is equal to L1 L2 sine 2. Okay, so it is L1 L2 sine 2, and it does not depend on theta 1 again. So L1 L2 are constants, so it doesn't matter. But what about sine 2? Sine 2 maximum value is 1, so max is 1. Okay, so which corresponds to theta 2 equal to 90 degrees and 270 degrees. Okay, so this is a very interesting proof, and very important proof in robotics. This is extremely important in robotics because where we should perform a task is where this angle here, so where the angle theta 2 becomes, this is my theta 2, and this becomes 90 degrees. So what are the two solutions? One solution is here, and the other solution is there. Okay, so this is my the other solution. This plus 90 and minus 90. Okay, so this is not really 90. So so let me draw it again in a blue color, and this is my one solution. Okay, theta 2 equal to 90, so this is 90. So where is the other solution? The other solution is here, where this arm is like this and this is like this. So this one is 90 now. Okay, or on this side it is 270. Now, so it should perform a task where the joint angle theta 2 is 90 or 270. Now, this is very interesting and very important. Why? I've said this quite a few times, because even as human beings, we have to perform tasks. So when we are, let's take the case of a human. We are performing a task. Okay, this is my hand. Okay, so when you're writing, for example, okay, so we are writing on a desk, you're sitting and you're writing with a pen. Okay, now if you look at this angle theta 2, you'll find that it is 90 degrees. Okay, so when we're writing, that angle in your arm is 90 degrees. Now what does this mean? This means that the energy requirement is minimum, right? Now if you think about it a little bit, that when you're picking an object or placing it, or when you're writing, essentially all of us can do it in different ways, isn't it? So our hand has 7 degrees of freedom, so it basically means that there are infinite solutions. This is the redundant system, right? So because it is redundant, we can get infinite ways of doing a task, but all of us do it in the same way. So when we are writing, we write in the same way. When you're picking up an object and keeping it somewhere, then you're doing it exactly in the same way. Okay, now why is that so? That is essentially because we do tasks are performed, are done based on energy minimization. Okay, so we do tasks in such a way that the energy is minimized, and we have evolved that way. So when we are doing a task, when we are walking, when we are picking up something, you always find that our energy is minimized, and this is an interesting proof that even we have to satisfy this. So if you look at our whole work volume, that's our work volume, right? Where are you going to perform a task? You'll perform a task where theta 2 is equal to 90 degrees, which is around in this region. Okay, so most of us do the task around this kind of regions, okay, in the center of the workspace. And for a robot also, when it is going to pick up and place something, for example, if I look at this robot, if it has to pick up and place something, it will normally pick up and place like this, pick up from here, keep it here, where it's so this is my elbow up and elbow down condition. So where it's going to pick up from here and keep it here, and that is what this proof also tells us. So we have answered two questions. The first question was that the singularity, that when determinant of j becomes equal to 0, it becomes a singular position. Then we looked at the other two conditions, that where should you perform a task? You should perform it where the energy requirement is minimum, and the energy requirement is minimum when theta 2 becomes 90 or 270. Okay, now these are two very important proofs. Now let us look at a very simple example where, so let's look at this example and try to understand the variation of of the energy as it is moving. So here we have a two-link manipulator. So these are two links. Okay, this is the end effector, and the manipulator has to trace a path like this. So this is a straight line path, and the manipulator has to trace that path. Okay, so what we are seeing is that when it is here, then the manipulator will be somewhere like this. When it is becoming stretched out, it is going to get more stretched out. So that is the way it is going to go, right? So what we are seeing is there is a change of theta, and if there is a change in theta, then the value of determinant of J is going to change. You know that. So now what is the question? The question here is, for this two-link manipulator, we want it to go from this point, from point A to point B, okay, from point A to point B, okay, and it should have, so manipulator should go move from A to B with uniform velocity of meter per second. Okay, so this is the problem. The manipulator end effector should move, so we can call it end effector, okay, should move from point A to point B with a uniform velocity of 1 meter per second. Now to achieve this, what is the joint velocities? Now the very interesting, the end effector velocity is constant. It's 1 meter per second, okay, in this direction. Now what is the corresponding joint velocity? Is it same? Is it also constant? No, it will not be constant. Why? Because it depends on theta now, and theta is changing. Now if you look at this manipulator, this is my theta 1, okay, and this is my theta 2. That's my theta 2, right? So what we can do is, the first thing we need to do is to find the Jacobian, then find its inverse. So this is a two-link system. So for a two-link system, we just derive the Jacobian. So how do we derive it? This is x and that is y. We just did it some time back. This is L1, this is L2, theta 1 and theta 2, right? This is my point xy. So we have seen that we can write the Jacobian as x dot is equal to x dot, the Jacobian x dot is equal to j into theta dot, and theta dot is what we want, which is equal to j inverse of x dot, right? And what is j inverse? J inverse we have seen is equal to 1 by L1 L2 sine 2, and then the adjoint of j, which is L2 cos 1 2, and this is L2 sine 1 2. This is minus L1 cos 1 minus L2 cos 1 2. This is L1 sine 1 minus L2 sine 1 2. Okay, this is the adjoint of the matrix J. So this gives us the relation. So on the left hand side, what do we have? Left hand side we have x dot. Now we have in this expression we have theta 1 dot and theta 2 dot. Okay, this is my left side. This is my matrix here. So it is 1 by L1 L2 sine 2. Then it is L2 cos 1 2, L2 sine 1 2 minus L1 cos 1 minus L1 minus L2 cos 1 2, and then it is minus L1 sine 1 minus L2 sine 2. Let me write this here. So L2 sine 1 2. This is the matrix. Okay, and this is my velocities x dot and y dot. Okay, so this is what I'm trying to find. Now we are given that x dot is equal to 1 meter per second, and we are given that y dot is equal to 0. Okay, because it is moving in a straight line along the x-axis. So it is moving like this, right? This is my x-axis. It is not going in the y direction. So this is my input. This is the input here. So I put it here. Okay, and what do we get is we get theta 1 dot is equal to C1 2. So let's go. We basically open this, so it becomes y dot is equal to 0. So this term will become 0. Okay, so theta 1 dot y dot is equal to 0. So I can put 0 in there. So what will happen? This part will become 0 and that part will become 0 both times in terms of x dot and in terms of theta 1 dot and theta 2 dot. Now what do we get is theta 1 dot is equal to C1 to x dot and L1 S2. This is because y dot is equal to 0. So the second term will go. Okay. Similarly, we get theta 2 dot is equal to, what is the term? It is C1 L2 minus C1 L2 sine 2 minus C1 2 L1 sine 2. Okay, which is this term. Okay, this term will both cases it will become 0. So this is our expression for x dot. Okay, similarly theta 2 is equal to this. Okay. Now what we are seeing here is that we assume that, so we are moving from one point to another point, right? We are moving from point A to point B. So at point A, what we can do is we have to find what is theta 1, theta 2. So when the manipulator is moving, it is moving from the fully stretched condition like this, it is moving to fully extended condition like this, it is moving like this. So this is my A, this is my B. Okay. So what we are doing is, this is my theta 1, this is my theta 2. Okay. So what we are doing is, at A location, what we are doing is theta 2 is approaching 358 degrees, let's say. Okay, so it is going on the other side. You can see it is here. So this is my 358 degrees. Okay, and theta 1 is equal to 1 degree. Okay, at location A. So what we'll get is these two values will be exceptionally high. So we'll get theta 1 dot. So at this location, when we put it back into our equation here, so theta 1 dot and theta 2 dot, if I put in these values here, okay, what we do get is theta 1 dot is equal to cos of 359 divided by 0.3 into sine of 358, which is equal to 95.5 radians per second. Similarly, theta 2 dot is equal to minus of cos 1 degree divided by 0.3 into sine 358 degrees. Okay, minus cos 359 divided by 0.3 into sine of 358, which is equal to 191 rads per second. Okay, so what we are seeing is that these values are excessively high. So what we can do next is, as it is coming closer and closer, the values of theta 1 and theta 2 will change, and as it is coming closer, what we will find is that the velocities are going to change. Okay, so as it is going, these values are high. Why? Because we are going near a singular point. This is a boundary singularity. So near a boundary singularity, what happens is the values tend to become very, very high. Okay, so something to note here is that, let me just change the color and explain this. So suppose we see the manipulator which is completely stretched like this. Okay, now in this location, what happens is theta 1 is equal to 0 and theta 2 is also equal to 0. Okay, now if I put theta 2, if I put cos of 1, 2 in this expression, okay, here, what is going to happen is it is going to become cos of 0 into x dot divided by L1 L of sine 0. Okay, and sine 0 is going to make it 0, and this will become infinity now. Okay, so what this is showing is that as we are going towards the boundary workspace, the boundary singularity in the workspace, the velocities are actually, velocity relationship is breaking down. Okay, this is an indicator that sine 2 becoming 0, theta 2 becoming 0 means that this relationship is breaking down. It's going to infinity now. Okay, so it basically shows that as you're going towards a singular position, your velocity goes towards infinity, And this is an example of this tool-link manipulator system that this problem indicates this. So there is another way of understanding how this behaves, how the Jacobian behaves. Okay, so this example basically showed that as you are stretched out completely in position A, your velocity is very high. If you are coming backwards towards position B, your velocity will decrease. Now it will decrease and then start becoming high again. Okay, this is an interesting thing. So this is where we come about a term which is called manipulation ability. So this is a term, a new term, which has to do with singularities and the Jacobian. So this is called manipulation ability, which basically means the ability to move. The manipulation ability is called the ease of moving in a particular direction. Okay, so how easily can you move in a particular direction is indicated by the manipulation ability. Now again, this is determined, this is dependent on the, so W is the manipulation ability, which is the determinant of J. Okay, so what we can say is the determinant of J is an indicator of how much energy is being consumed. It is also an indicator of the direction in which you can move. Okay, now what does this basically mean? Now this is for a non-redundant system. Okay, non-redundant system means that J is a square matrix M into M. Okay, now W is equal to the square root of determinant of JJ transpose for a redundant system. The redundant system means, for example, if the degrees of freedom are greater than 6, okay, then it's a redundant system. So in that case, what will happen is J is non-square, it becomes M into N. It is a non-square matrix. So this basically gives us an indicator of the ease with which you can move in a particular direction. Okay, and this is called our manipulation ability. Now let us understand this graphically. So when I'm, as we saw in this earlier example, this example that we solved, as this is stretching out and becoming straight, your velocity is going towards infinity. Okay, your joint velocities, which means in the fully stretched condition, if I want to move in this direction, let me draw it here. Okay, let me draw it again here. So we have a manipulator like this. The manipulator is in this configuration. Okay, and then it is fully stretched in this configuration. So we are fully stretched here, and then we are bending. Now in the full stretch condition, we have seen that your velocity will go to infinity. Now what that basically means is that you cannot move in this direction. So you cannot move, no motion, sorry, I won't say no motion, it is difficult to move in this direction. Difficult to move in this direction, right? But it is easy to move in that direction. Okay, so this is an indicator of ease of motion. So in the workspace, both directions are not equally easy to move in, depending on where you are. Okay, this is something very interesting to note, that in this configuration, it is very easy to move in this upwards, but it is difficult to move like this. Okay, now why does that happen? Is because this determinant of J can be expressed as an ellipsoid in space. Now this determinant of J is basically giving us a transformation between x dot is equal to J into theta dot. Okay, so what is J doing? J is transforming theta dot into x dot. That is what J is doing. And J is a 2 by 2 matrix which has, so if you look at this transformation, what it is basically doing is, our input is a unit sphere and the output is an ellipsoid. Okay, so this is my unit vectors u, this is my unit vectors vt, and this is my rotated system like this. Okay, this is my v, this is u. Okay, so what is this transformation J doing? So this transformation J is rotating the axis system. So it is here it was straight, you can see it is this direction. It has rotated this and made it U, okay, and it is scaling it. So it is doing two things. First thing what J is doing is it is rotating, and number two, what it is doing, it is scaling. Okay, so we can think of it this way, that we have the motor being fixed onto the joint, and we are going to give a joint velocity. We're giving voltage, we're giving joint velocity theta dot. Okay, now this theta dot, and if we say that, if we normalize the joint velocities and say that theta dot mod of theta dot is less than or equal to 1, so we are normalizing it. So whatever is the maximum velocity that is possible for the motors, for all the motors, we are normalizing it and saying that it is less than or equal to 1. Now this is expressed as a sphere in three-dimensional space, in not three-dimensional space but in n-dimensional space. Okay, so if the robot has n joints, then it is an n-dimensional space. So this one is the equation of a circle in 2D. In 3D it's a sphere. Okay, so this is essentially like this. What is the axis? The axis are Vt in this direction. Okay, that is my velocities, the input. Now what is J doing? It is rotating this axis system. So it was Vt, it has made it U like this. Okay, it has rotated by some angle, and what it has done is it has scaled it, means it has stretched it in some direction and shrunk it. So in this direction it has stretched, in this direction it has shrunk. Okay, so this is an interesting transformation, that x dot is equal to J into theta dot. Okay, what it does, it takes a sphere and stretches it and makes it into an ellipsoid. Okay, this is what it is doing. Now the initial is Vt and the axis is U there. Okay, now how can we represent this graphically? What we basically understand is that if you take the singular value decomposition of J, okay, you can divide this matrix J into three matrices. It is U, sigma and Vt, where U and sigma are called orthonormal matrices. So orthogonal matrices. Okay, matrices, and this is called a diagonal singular matrix. Diagonal matrix containing the singular values. So it is sigma 1 and sigma 2, 0, 0. In the case of a 2D, this is 2 by 2 we are talking about, so it is like that. Okay, now what is sigma 1 and sigma 2? Sigma 1 and sigma 2 are what we call singular values. Singular values are equal to the square root of the eigenvalues of the matrix. Okay, so I use the term singular value. You may not be familiar with that, but you're familiar with eigenvalues. Okay, so now this basically is telling us that this J, what it is doing, it is rotating and it is scaling the joint velocities and making it into your end effector velocities. Right, now what is Vt and U? Vt and U are the orthogonal matrices. So this is the unit vector, these are the basis vectors. Okay, so before transformation it was in the direction Vt, and after transformation it has gone in the direction U. Now orthogonal basically means that U is equal to U transpose and Vt is equal to V, the inverse, inverse is equal to this, and Vt inverse is equal to Vt. The inverse is equal to, what did I write? So V inverse is equal to V transpose. Okay, and sigma 1 is the major axis of the ellipse, and sigma 2 is the minor axis of the ellipse. Okay, what is the major axis and minor axis? Let us look at this again. So what we are saying is that this transformation here, which transformed the circle into an ellipsoid in n-dimensional space, this is my sigma 1 and that is my sigma 2. Okay, the values I mean. and the axis is u, and here it is vt. Okay, so this is showing that velocity at the joint is getting transformed into an ellipse at the end effector. Why? Because our transformation x dot is equal to j into theta dot is of this nature. Okay, and we can find this by looking at the singular values, which are the square roots of the eigenvalues of the matrix J. Now, what does this mean? Sigma 1, sigma 2 again. Now, sigma 1 and sigma 2 is essentially indicating velocity, okay, in magnitude, velocity in magnitude. Okay, and u is giving direction. Direction in space. Okay, so now this is very interesting, that if your input is a unit sphere, then your output is an ellipsoid. So what it means is that at the joint velocity, okay, this is my joint velocity. If my input to the joint, here I'm giving the voltage to the motor, and we are giving a velocity here, theta dot. If this is a unit sphere, okay, this is my theta dot, the output at the end effector x dot and y dot belongs to this ellipsoid. So which means that it is going to have a particular shape. Okay, and when we are fully outstretched like this, this ellipsoid is going to shrink and it will become a straight line. So what this means, that your determinant of J, okay, sorry, your matrix J is a function of sine. There is sine, and we have seen this values, minus L1 cos 1 minus L2 cos 1 2, L1 sine 1, sorry, and this is L2 cos 1 2. This is L1 sine 1, and this is L2 sine 1 2, and this is L2 sine 1 2. So we have theta 1 and theta 2. So when the manipulator is moving in space, theta 1 and theta 2 is changing. So if this is changing, then this value is changing also. Okay, so when this matrix value is changing, what is happening is, when you take the singular value decomposition of J, then the values of sigma 1 and sigma 2 are also changing. Okay, and similarly your VT is, your U is also changing. U is the direction in space. Okay, so this basically means that when we are moving in space, the direction of sigma 1, sigma 2 and the magnitude is changing, which means that your ellipse is changing shape as well as direction as we are moving in space. This is something a little difficult to understand, but it's very, very important that we can take the singular value decomposition of J, and this basically gives us U sigma Vt, and this fellow determines this is your matrix, which consists of sigma 1 and sigma n actually. So sigma 1 is the largest and sigma n is the smallest. Singular values. Okay, so this is basically telling us the magnitude of the ellipse, the major axis, minor axis, and it is also telling us the direction of the ellipse. So when we look at this manipulator here, let's look at this example. This is an interesting example, that suppose you're moving in a straight line like this. Okay, so I'm going to move this manipulator in a straight line like this. So when we are somewhere here, okay, my manipulator is like this, the direction of my ellipsoid is going to be like this. Okay, we can find this out. We know what is J. So for doing inverse kinematics at every point here, we can find what is the corresponding theta 1, theta 2. Then I can put this in the matrix J and find what is the, do SVD of J and find what is sigma 1, sigma 2, and also find what is U, right? And then I can plot the ellipse. So this is my direction. Okay, now as we are going this side, what is happening is the ellipse is becoming bigger like this, and somewhere in the center it tends to become circular. Then that is in the center somewhere here. Okay, so this is meaning in the center, center of workspace. What is the meaning of center of workspace? When theta 1 is equal, when your theta 2 is closing to 90 degrees. Okay, that is the configuration in which sigma 1 will tend to become equal to sigma 2, and which means this will become, ellipse will tend to become a circle. Okay. Now, what does the meaning of becoming a circle? A circle basically means that you can move, a circle is like this. So if sigma 1 is here and sigma 2 is here, then sigma 1 is equal to sigma 2, which means you can move in all directions easily. Okay. Whereas as we start going towards this side, so this is at the center of the workspace, as we are moving more and more this side, so what the manipulator is doing is it is stretching out. So if you can imagine, it is here, it is stretched out like this, and then it's stretching out even more. Okay, so the manipulator is stretching out. It is here. Okay, now it has gone even more here. Okay, it is becoming straight. What we'll see is that the ellipse will start becoming from a circle in the center. It will start becoming ellipse. It will start becoming shrinking again. So what is going to happen is going to become narrow and thin, and at the end of the workspace, it will become a straight line. Okay, so this is something very interesting to note, that if I draw it in a larger scale, okay, so this is my, so in a larger scale, if I draw it, then this is my ellipse, this is my manipulator. When it is fully stretched, it is somewhere here, okay, fully stretched manipulator like this, okay, and in this configuration, it is somewhere here, okay, it is somewhere here. Now, as the variation of theta 1 and theta 2 takes place, what is happening? There is an ellipse like this. This is an ellipse. Okay, this is my major axis, that's my minor axis. Towards the center of the workspace, when this one is 90 degrees, okay, when theta 2 is 90 degrees, this ellipse will tend to become circular. Okay, so this is my sigma 1, sigma 2, major axis, minor axis. Then as it starts moving this side, what will happen is this will start shrinking into an ellipse. It will become like this. Okay, so this is becoming from a circle, it is becoming an ellipse. More and more is becoming thinner, and here it is becoming like this, and finally when it fully stretches out, it will become like this. Okay, so what we are seeing is, what is changing is the values of sigma 1 and sigma 2 are changing, and this is magnitude. Sigma 1, sigma 2 is magnitude and direction of so this is my direction. So I can move, in this case, I can move in this direction. Okay, that means x dot, my velocity is in this direction is okay, but I cannot move in this direction. And that we saw in the example we did some time back, that if it becomes in singular configuration, what will happen? The velocity will become infinity. Okay, now in the and it's very interesting that at theta 2 equal to 90, okay, your sigma 1 will become equal to sigma 2. Okay, it should become somewhere equal to, it will not be exactly equal, but it will become more or less a circle. So this is also indicator of the direction in which you can move in space very easily, and this is basically called the manipulation ability ellipsoid, and it is an indicator of the direction in space where you can move very, very easily. Now if it is a circle, so we are here and the ellipsoid here is circular, so it basically means that you can move very easily. Sorry, it's not exactly a circle, but it will be something like a circle. So it basically means that you can move very easily in all directions, in this direction, this direction, this direction, this direction, this direction. And our sigma values, so this is my sigma 1 and this is my sigma 2. So sigma 1 is almost equal to sigma 2. Okay, now you can note that this angle is 90 degrees. So which means that this is also the best place for performing a task. So if you're performing a task where theta 2 is 90 degrees, you can move equally in all directions. Okay, now I would, this is mathematically proved. Okay, I just did the how this is proved. What is the meaning of J? What is the singular value decomposition of J? Okay, and how does this affect the direction in which you can move in terms of the velocities? Now, as a very simple experiment, you can do this very simple experiment, and it's very interesting and important because human beings are also mechanisms, right? Our hands and legs are also mechanisms. So do this very simple experiment. So you have your hand like this, okay, move your hand outwards. Okay, what I mean is you fully stretch your hand. So when your arm is stretched, it comes like this. Okay, this is fully stretched arm. Okay, so your arm is fully stretched in this configuration. Now in this configuration, this is two links. Okay, so these are your two links now. So this is your theta 1, this is your theta 2. in fully stretched condition. Now if you try and move this side, you'll find that you will not be able to move this side. Okay, it is like it is locked there. Whereas if you move this side, it is very easy to move this side. Okay, please do this experiment by yourself and you'll be convinced of the maths part. Okay, so in this configuration, it is not, you cannot have a velocity in that direction because at that point it is locked. Okay, it's a singular point now. And the direction of the velocity ellipsoid says that there is no sigma 2 is 0 here now. Only sigma 1 is there. And it means sigma 1 is in this direction, so you can move up and down, but you can't go this way. Okay, whereas in the center of the workspace, you can move equally in all directions. Please bring your hand to the center of the workspace where your theta 2 is 90 degrees. So this angle is 90 degrees. Okay, and then you'll see that you can move equally in all directions very easily because the shape of the ellipse is circular. Again, when you're folding and coming like this, so your arm is folded and it has become like this. Okay, now again the ellipse is like this. So you can see that you can move easily in this direction, but you'll not be able to move easily in the backward direction. This is an indicator that even for our hand, this is valid. Okay, so today we talked about Jacobian, and the Jacobian gives us the relationship between the end effector velocity and the joint velocity. It also gives us an indicator of the energy. It tells us about singularity, and it also tells us where of the manipulation ability, the direction in space where we can move easily and the direction in space where we cannot move easily. Okay, so the Jacobian is a very, very important matrix, and it is used to determine not only the singular positions, but also to look at concepts of energy consumption, direction in space which you can move, and so if you're trying to move in a particular direction very quickly, okay, you have to find the ellipsoid in that position and then see where are the directions of sigma 1 and sigma 2. So if you find that your sigma 2 is becoming 0, then you can't move in that direction. Okay, so it's very interesting that you could be inside the workspace, but there could be regions inside the workspace where you cannot have very high velocities. Okay, that is again determined by the singular values of J. So we'll stop here today, and then we'll also see that the Jacobian is also relating the end effector forces to the joint torques. This is because the velocities and forces are related in the physical world, right? So the Jacobian also relates the end effector force with the joint torques. So that we'll be looking at in the next class or after a few classes. So we'll stop today. Thank you.